Hey everyone, having a little bit of technical difficulties, so I had to start the stream a little early today, but we're still going to wait until 10:40. So if you're watching this later, you're just going to have to fast forward a few minutes. Hey, for those who are joining us, we're still just going to wait a couple minutes until 10:40, 10:41 or so. Welcome. Good morning. 10:41, but it looks like we currently only have about 53 people logged on. So I'm just gonna wait 1 minute and then we're gonna start with a little review. So if people tune in late, that is not a big deal. Okay, I'm going to go ahead and get started. First, there was a question in the chat about when you're doing yield and limiting reactants and there are multiple products, which product you should use. It depends exactly what the question is. So if you're just trying to figure out limiting reactant, then what you want to know is which reactant is going to run out first. So you can pick whichever product you want to calculate how much product you could form. But with yield, the problem would need to specify what is the yield of CO2, what is the yield of B, because you can have a different yield. Since yield is in units of grams, if you have different stoichiometric coefficients for different products, you'll have different yields. So for yield, it would need to specify. So today we're going to talk about redox reactions, but before we get into that, I just wanted to do one last review of line drawings. After going through the submissions for problem set 6, it seems like this is still a tripping point for a lot of people. So I just want to one last time go over the rules of how to read line drawings. And if you're still confused, ask questions and come to office hours and we'll help you out. So the two basic rules of reading these simplified line drawings is that everywhere a bond is drawn, where it ends without specifying what element it's ending in, that's a carbon. And then for every carbon that doesn't have 4 bonds, we add enough hydrogens to make sure there are 4 bonds. So this is an example from the homework. So everywhere that a bond ends, so I've circled everywhere bonds end, that's a carbon. So that means that there are 9 carbons. So this molecule is going to start with C9. And then we need to figure out how many hydrogens there are going to be. So this carbon on the end only has 1 bond coming to it. So it needs 3 more hydrogens. And then most of our other carbons need 1 more hydrogen because they all have 1 double bond and 1 single bond. So they have 3 bonds and they need 1 more. The exception being that carbon in the middle there that's coming off the ring. It already has 4 bonds. It has the double bond coming down and then 2 single bonds. So it doesn't need any any more hydrogens. And so we can count how many hydrogens that is. And so this molecule is C9H10. So if this is something that is still tripping you up, that's fine. It is kind of confusing because it's sort of like, why did we pick carbon? And the answer is really just because it's so common that that's the one we got the most tired of drawing. But it definitely can be confusing, and it's something that just gets a lot easier with practice. And one thing I wanted to say is that the only elements that are invisible in these line drawings are carbon and hydrogen. So if there was, say, an oxygen, that would be drawn. There would be a letter O. So if there's no letters at all, that means you only have carbon and hydrogen, and then any other elements that could be bonded in there will be drawn. So there could be like an OH on the end. So yeah, I hope this helps a little. It's definitely something that you just get better at with practice. So definitely don't feel bad if this is still challenging, but do let us know if there's anything that's unclear, if you have any questions. Okay, so today we're going to talk about oxidation and reduction. So the basic definition of oxidation is loss of electrons. So if a given atom loses electrons, it has been oxidized. And when you lose electrons, electrons are negatively charged, so your charge is now less negative or more positive. So if something is oxidized, it loses electrons and its charge becomes more positive. The opposite of oxidation is reduction. So reduction is the gain of electrons. If you gain electrons, those are negatively charged and your charge becomes more negative. The way that I remember this is this acronym oil rig. I don't know if that's what everyone uses, but Dublin Kaufman High School in 2010 has stuck in my mind, and this is how I remember it. I literally say this in my head every single time I solve a redox type problem. So oxidation is loss, reduction is gain. And the implication is of electrons. So reduction is loss of electrons, oxidation is loss of electrons, and reduction is gain of electrons. So I don't really like memorizing things, so I like having little acronyms that help me. So this is mine for this. The problem here is that not everything is charged explicitly. And so instead of pretending things are charged that aren't, we use what's called an oxidation number. So we can assign an oxidation number to every single atom within a molecule, and doing that lets us keep track of electrons. So we'll go through sort of the rules for how to assign these numbers in a minute. But basically the point of an oxidation number is to tell us how many electrons has this atom gained or lost. That said, if something is charged, the oxidation number will be equal to the charge. So if I have a lithium plus ion, its oxidation number will be +1. So if you have something that's charged, there's kind of no need to distinguish between oxidation number and charge because they'll be the same. But if you have more complicated molecules, even like H2O, none of those are explicitly charged. They're not ions, but they still have oxidation numbers. And so just to expand on our definitions from the previous slide, oxidation increases the oxidation number, and reduction decreases or reduces the oxidation number. So that kind of makes sense to me. If you oxidize something, its oxidation number is its extent of oxidation, and that number goes up. Okay, are there any questions on just the definition of oxidation or reduction or oxidation number? Okay, if any more questions come up, obviously, please put them in the chat as soon as you think of them, and I will answer them. So there are a lot of rules behind assigning oxidation numbers, and they can get kind of confusing. So I'm sorry, here are some cute penguins as apology for all of the text and rules that are going to be on this slide. This would be a good slide to take some notes. So the first rule is that any element not bound to any other element will have an oxidation number of 0. So if I have solid aluminum metal that's uncharged, it's going to have an oxidation number of 0. If I have an O2 molecule, which is oxygen is bound to something, it's bound to another oxygen, but it's not bound to another different element than itself, then the oxidation number of both oxygen atoms is 0. And the way that I think about that is just that those two oxygens in my O2 molecule are equivalent. So it wouldn't make sense for one of them to be +1 and one of them to be -1. They have to be the same. So that's an important rule that will always be true. Hydrogen is almost always at +1. There are a few special cases where it's bonded with metals where it's -1, but most of the time it's at +1. The oxidation number of elements in group 1 and 2 is equal to their group number. So this kind of goes back to what we were doing a long time ago with ions and ionic bonds. So if you look at those first two groups in the periodic table, that first group is going to have an oxidation number of +1, and the second group is going to have an oxidation number of +2. And that should kind of make sense if you go back and think about valence electrons. Lithium has one valence electron, it wants to lose that electron and become +1. Fluorine is always -1. And yes, there's a question in the chat, oxidation is loss of electrons, right? Yes, exactly. I always keep saying oil rig in my head repeatedly. Oxidation is loss of electrons and reduction is gain of electrons. So sodium Na has one valence electron. It wants to lose that valence electron, become oxidized, and have an oxidation number of +1. However, if we have sodium metal that's uncharged, if we go back to rule 1, it's going to be an oxidation number of 0. So I guess I should specify that rule 1 is always true, and then all these other rules are for when there's bonding going on. So then other halogens, so that's that second to last group on the left, so bromine and others, they're have an oxidation number of -1 unless they're bonded to oxygen or a halogen that's in a higher row. But for the most part, they're going to be -1. And then oxygen is almost always -2. Again, there's a special case like if fluorine is bound to oxygen, that changes, but that's not going to happen that often. So like the vast majority of the time, you can just remember that oxygen is -2. And then the last rule is that for any compound, the sum of all of the oxidation numbers of all of its atoms will be its charge. So if it's a neutral molecule, like most of the molecules we'll be talking about are, then that must be 0. So if I'm looking at H2O as an example, I have 2 hydrogens and 1 oxygen. That hydrogen is going to be +1 and the oxygen is going to be -2. And we have 2 hydrogens that are each +1 and we have an oxygen that's -2, so that adds up to 0. So we have -2 + 1 + 1, that adds to 0. Okay, so this is a lot of, so if I had a molecule that had a net negative charge, then all those oxidation numbers would need to add up to whatever the charge is. Okay, this is a lot of rules, so I'm just going to pause and see if there are any questions about what these rules mean. Really, the most important rules are that if there's an element in its elemental form where it's not bound to atoms of any other element, the oxidation number of all those atoms is 0. Hydrogen is basically always +1, oxygen is basically always -2, and then the summing of the oxidation numbers of all atoms in a molecule has to be equal to its charge. The other rules are, true and important, but if you remember just those 4, it'll get you pretty far. Okay, I'm just going to pause a little bit more for questions. Why is the oxidation number of H2 0? So for that, you look at the first rule. So the rules number 2 and onwards apply when there's bonding between different types of elements. But the first rule is always true, so that hydrogen is not bound to any other element. So each hydrogen has to have an oxidation number of 0. So the way that I think of that is like if you look at that very last rule, so H2 is uncharged, so that means that the sum of the 2 oxidation numbers of the 2 hydrogen atoms has to be 0. And those 2 hydrogen atoms are totally equivalent to each other. And so it would not make sense to have one of those hydrogens have an oxidation number of +1 and one to have an oxidation number of -1 because they're the same. So the only way that they can add up to 0 while also being the same as each other is if they are both 0. There's a question about like what defines halogens. So halogens are that second to last group, that second to last column on the periodic table. So they start with fluorine, and then I think bromine is next. It's that second to last one. And if you think back to when we were talking about valence electrons, they have 7 valence electrons, and so they're going to want to gain one more electron in order to then have 8, and then that would get them to an oxidation number of -1. So they've gained an electron, they've been reduced, and their oxidation number has gone down. So yeah, those halogens are like bromine down on that second to last column. Yes, so rule 1 overrules that second to last rule about oxygen. Rule 1 is kind of like a separate category from the other rules. I probably should have written this differently. Rule 1 applies when there's no bonding to other type of elements involved, and all the other rules except the last one are when there is bonding with different types of elements. So any element, including sodium, lithium, whatever, when it's uncharged and not bound to any other type of element, will have an oxidation number of 0. So oxygen, hydrogen, everything. And then when oxygen is bound to anything else except fluorine, it will have a charge of -2, or sorry, an oxidation number of -2. Okay, so keep asking questions if you have them. On the next slide, I've put more cute animals because I know this is kind of tricky. I've kind of compressed the rules over to the side, and then I have a lot of practice over here. So I want you in your breakout rooms to take some time. I'll give you kind of a lot of time because there are a lot of molecules here, to think about how you would assign the oxidation numbers to each atom. So you're not looking for the overall oxidation number of the compound. You want, like, in H2O, what is the oxidation number of H? What is the oxidation number of O? Okay, so take some time in your groups. I'll give you probably like 5-10 minutes because there are a lot here. And as always, please keep putting questions in the chat. So there's a question in the chat that says, do you add the oxidation numbers? So in order to follow the last rule, yes, the sum of all of the oxidation numbers of all of the atoms will be its total overall charge. So for H2O, I have 2 hydrogens and 1 oxygen, and the overall molecule is neutral. It has a charge of 0. So I need to follow the middle rules to assign the oxidation numbers of H and O, but then I need to make sure that 2 times the oxidation number of hydrogen plus the oxidation number of oxygen will be 0. So for SO4, this last one, you need to make sure that the oxidation number of sulfur plus 4 times the oxidation number of oxygen, since you have 4 oxygens, that all needs to add up to -2. So yeah, that's what the last rule is telling you to do. We'll go over the examples in a minute, but number of +1, but we'll go through the answers to these examples in a minute. How to find the oxidation number of carbon? So you need to use the last rule. So you can tell what the oxidation number of oxygen will be from the second to last rule. And then you need to use the last rule to figure out what the oxidation number of carbon needs to be such that the total oxidation number is 0, because CO2 is neutral. So you want the oxidation number of carbon plus 2 times the oxidation number of oxygen to equal 0, because the molecule is neutral. Yeah, okay. So let's just come back together and I'll go through the solutions here, and then if there are questions about how I got to those solutions, please ask them. So for H2, we're going to use that first rule. So hydrogen is only bound to another hydrogen, and so both hydrogens have an oxidation number of 0. For H2O, we can use both the hydrogen and the oxygen rules. So hydrogen will be +1 and oxygen will be -2. So based on that last rule, we need 2 times +1 plus 1 oxygen, where the oxidation number is -2, to equal 0. So 1 plus 1 minus 2 equals 0. And then this is the question in the chat. So for CO2, my oxidation number of oxygen is -2. I have 2 of those and only 1 carbon, so my oxidation number of carbon needs to be +4 in order for that last rule to be satisfied. So -2 plus 4 equals 0. For MgCl2, we're using 2 rules. There's the halogen rule and the rule about elements in groups 1 and 2. So magnesium is in group 2. It's going to have an oxidation number of +2. And you could figure out the oxidation number of chlorine just from that by the same rules we've been using above. Or you can know that chlorine is a halogen and it's going to have an oxidation number of -1. And so again, +2 minus 1 is 0. So going to the question in the chat about Na versus Cl, so Na is in the first group, So we're going to use that group 1 and 2 rule. So Na will have an oxidation number of +1. And another way to think about that is going back to valence electrons. So sodium is going to have 1 valence electron. It's going to want to lose that electron. And then because the electron is negatively charged, that will make its oxidation number +1. So I think that can be a little confusing for people because you're losing an electron. So that makes you think like some number should go down. But since electrons are negatively charged, your charge is going up, your oxidation number is going up. For Cl2, we go all the way back to rule 1. So the chlorine is only bound to other chlorines, and so it therefore will have an oxidation number of 0. Both chlorine atoms will have an oxidation number of 0. These last two get a little bit tricky. So for P4O6, my oxygen is, like I said, my rules say that oxygen is almost always -2, except when it's bound to fluorine. Phosphorus is not fluorine, so oxygen is definitely going to be -2. So that part's easy. And then we need to use our last rule. So we know that the sum of the oxidation numbers of all of its atoms must be equal to its charge, and its charge is 0. So 4 times the oxidation number of phosphorus plus 6 times the oxidation number of oxygen, which is -2, will equal 0. And so then all we have to do is solve that equation. We're going to get 4 times N equals 12. 12 divided by 4 is 3. So our oxidation number of phosphorus is going to be +3. And then this last one is probably the hardest. So again, oxygen is going to be -2. It's bound to some kind of element other than itself. It's bound to sulfur. And then it's not bound to fluorine. So our oxygen is definitely going to be -2. And then we're going to do exactly the same thing as we did above. So we're going to say the oxidation number of sulfur, there's only one of it, plus 4 times the oxidation number of oxygen, since there's 4 oxygens, will equal to our total net charge of our molecule, which is -2. So that means our oxidation number of sulfur will be +6. Okay, I'm going to give you a couple minutes to go back to your groups and talk about whether this makes sense, whether these answers agree with what you got, and if you guys have any questions. So I'm going to give you like 2 or 3 minutes to chat in your groups and just make sure that everybody in your group feels okay about assigning these oxidation numbers, and if you don't, say something in the chat. So there's a question in the chat about P4O6. So we know that oxygen needs to be -2. It's bound to something other than itself, and that something is not fluorine. So oxygen is -2. That part is pretty easy. And then we need the total oxidation number, the sum of the oxidation numbers of all of the atoms, to be 0 because it's a neutral charge. So I have 4 phosphorus atoms, so 4 times the oxidation number of phosphorus, and I have 6 oxygen atoms, So 6 times the oxidation number of oxygen needs to sum to 0 because 0 is the charge of the overall compound. So I'm just going to solve the algebraic equation. 4 times n plus 6 times minus 2 equals 0. And if I solve that, I'm going to get n equals plus 3 for phosphorus. Okay, so there's 2 more questions in the chat. For the last one, we are adding up to minus 2 instead of 0 because of the charge of minus 2. That's exactly right. So the compound has a total charge of minus 2, and our last rule says that the sum of the oxidation number of all of the atoms will be the charge of the compound as a whole. So this kind of answers the last question in the chat too, which is what's the oxidation number of the whole compound? The oxidation number of the whole compound is just going to be its charge. So we really only specifically think about oxidation numbers of atoms. When we're thinking about the whole molecule, all we care about is what its charge is. So if you wanted to think about the oxidation number of CO2 or MgCl2 or any of these compounds, the total is going to be the charge, which is 0. And then, so you're really just going to sum up the oxidation number of the various atoms. And that's, by the last rule, is going to get you the charge. The oxidation number has, I don't think it has like explicit limits. I've definitely seen oxidation numbers of like +7 is definitely a thing. So I would be concerned if I was doing a problem and got an oxidation number of like 12, but that doesn't mean it's not possible. Typically, because it has to do with valence electrons, it's almost always like between -7 and +7. But there are weird cases that are outside that. But almost always it's going to be like somewhere between +7 and -7. I think if you got a number that was outside of that, I would just like check your work to make sure, but that's not to say it's like impossible. How would you determine the oxidation number with just the periodic table? So you can't always, but it does kind of go back to our discussion about valence electrons. So elements that are in that first group, we know that they have 1 valence electron, and so they're going to want to lose that valence electron, become oxidized, and have a +1 oxidation number. Similarly, in group 2, they have 2 oxidation numbers. They're going to want to have an oxidation number of +2. And then in that last group, they have 7 valence electrons. They're going to want to gain 1 more and have an oxidation number of -1. So you can use the periodic table for some elements like that to help you remember. But if I just told you, like, what's the oxidation number of copper, you can't know that without knowing what it's bonded to. As far as keeping track of electrons, we're going to get to that in just a minute, so hold that thought. But basically the point of redox reactions is that electrons are being transferred from one thing to another. So hold that thought for 1 second, we're going to get to reactions. +2 or 2+, so that's just a convention. People will know what you're talking about if you flip +2 and 2+. Typically, our convention is that we write oxidation numbers as +6 or +2 or -1. So we put the sign before the number. So the oxidation number of oxygen is -2. But then when we're talking about the total charge of SO4, we put 2- instead of -2. But like, that's fine. If you put -2 instead of 2-, everyone will know what you're talking about. Like, that's fine. But this is just a convention of how we typically write it. Okay, so keep asking questions, but I'm going to go on to the next slide to answer this question in the chat about keeping track of electrons. And then if this doesn't answer your question, ask it again, and I will clarify more. So, like I said previously, oxidation increases the oxidation number. And what that means in practice is that if something is oxidized, it loses electrons, and that means its oxidation number goes up. If something is reduced, it gains electrons and its oxidation number goes down. But the total electrons will be conserved. So we're not going to just have like electrons coming off of our compounds and floating off into the air. And similarly, we can't have electrons just appearing out of thin air in our reaction. So what that means is that whenever anything loses electrons, something else has to gain those electrons. So if something is being oxidized, something else needs to be reduced. So when I'm being oxidized, I'm losing electrons, and somebody else has to gain those electrons, or else they just disappear into thin air, and that's not how this works. So translating that into chemistry language, if something is oxidized, it reduces something else by giving it electrons, and therefore it's called a reducing agent. And conversely, if something is reduced, that means it gains electrons, which means it has to steal those electrons from someone else, thereby oxidizing that other thing. So therefore it's called an oxidizing agent. So just to sort of say that all again, if something is oxidized, it reduces something else by giving it the electrons that it is losing, and is called a reducing agent. So if I ask you, what is the reducing agent in this reaction, you need to find the thing that has been oxidized. That is the reducing agent. And similarly, if something is reduced, it has gained electrons, which means it has oxidized something else by stealing those electrons, and therefore it is called an oxidizing agent. So the thing that's oxidized is the reducing agent, and the thing that's reduced is the oxidizing agent. I'm going to pause for questions, because I remember being super confused by that terminology when I first learned this. I'm going to go through my example, but please keep putting questions in the chat if you have them. So here is an example reaction. So I have 2H2S plus SO2 going to 3S plus 2H2O. Going back to a couple days ago, this reaction is balanced. I have 3 sulfurs on each side, I have 4 hydrogens on each side, and I have 2 oxygens on each side. So if I want to figure out what's being oxidized and what's being reduced, what's the oxidizing agent, what's the reducing agent, I first need to assign oxidation numbers to each atom in these molecules. It is kind of counterintuitive, but I'm hoping that this example will kind of make it make sense. So if we're assigning the oxidation numbers here, we know that hydrogen has to have its +1 oxidation number, and sulfur therefore needs to be -2. So H2S is overall neutral, so we need 2 times +1 plus -2 equals 0. So hydrogen's +1, sulfur's -2. Looking at SO2, we know that our oxygen is -2, and we have 2 of them, and SO2 overall is neutral, so that means sulfur is +4. And then looking at our product side, our sulfur is not bound to any other type of element, so it has an oxidation number of 0. And then looking at H2O, our hydrogen has +1, and oxygen has -2. So that is just how we assign the oxidation numbers. That's the first thing we have to do before we can even think about which is the oxidizing agent and which is the reducing agent. So that's like always step one in this, is assigning those oxidation numbers, which is why we did that a couple slides ago. Okay, so now to figure out which is oxidized and which is reduced, if I look at the hydrogen and oxygen, they're +1 on both sides and -2 on both sides. So what I'm really looking at, the thing that's oxidation number is changing is sulfur. So if I look at H2S, the sulfur goes from -2 before the reaction, and it ends up at 0 after the reaction. So that means the sulfur goes from -2 to 0, which means its oxidation number goes up, which means it's oxidized, and therefore is the reducing agent. I'll go through again how I remember that. And then for SO2, it's the opposite. So our sulfur is +4 in SO2, and those sulfurs end up at 0. The oxidation number decreases, so SO2 is reduced, and SO2 is the oxidizing agent. So what's really happening here is that SO2 is stealing electrons from the H2S. So the sulfur in H2S was -2 and ends up 0, while the sulfur in SO2 is +4 and ends up at 0. So electrons are being transferred from the sulfur in H2S to the sulfur in SO2. So what that means is that SO2 is stealing electrons and that H2S is giving those electrons. So H2S is oxidized, and by being oxidized, it's reducing SO2. So H2S is the reducing agent because it is reducing something else by being oxidized itself. So I hope that makes sense, but it's also just like something that practice will get you, and you just kind of need to remember that we kind of crisscross. So whatever is oxidized is the reducing agent, and whatever is reduced is the oxidizing agent. So yeah, someone in the chat put in a different acronym that works for them. So lose electrons is oxidation, so that's LEO, and gain electrons is reduction, that's GER. If that works better for you than oil rig, then remember it that way. That there's like no like correct way to remember it. It's just that oil rig, oxidation is lost, reduction is gain, has been burned into my brain. But if you remember it a different way, as long as it works for you, that is totally fine. Okay. So I have a few practice questions that I want you to work on in your groups. So identify the oxidizing and reducing agents in the following reactions. So the first thing you're going to do is you're going to assign oxidation numbers to each atom, and then whoever's oxidation number goes up is oxidized, and whoever's oxidation number goes down is reduced, and then whoever is oxidized is the reducing agent, and vice versa. Okay, so I'm gonna give you a little while in groups. Yeah, so you're looking at the reactants and how they change. So one of the reactants are going to be the oxidizing and reducing agents, but you need to know what they turn into to see how the oxidation number has changed over time. From reactants to products. But yeah, it'll be either a reactant or a product that is, it'll be one of the reactants that is the oxidizing agent, and another reactant will be the reducing agent. More minutes, if that sounds okay. We'll come together at like 11:35. Let's take like 15-20 seconds to finish your thought and come back together. If you're not done, especially with the last one, that is okay. Okay, so the first thing that we need to do, always with redox reactions, is to assign oxidation numbers. I'll point out that, so for the first reaction, Mg and Cl are both 0 at the start, so they are not bound to any elements other than themselves, and so they have an oxidation number of 0. And then looking at the product side, magnesium is +1 and Cl is -2. So what that means is that Cl, chlorine, its oxidation number goes down, so it's reduced and is therefore the oxidizing agent because it is oxidizing magnesium. Magnesium is oxidized because it is reducing Cl2 by giving it its electrons. So similarly for this next one, these guys, so zinc is 0, it's not charged and it's not bound to anyone else. Copper is not bound to any other elements, but it is charged, so it has a +2 charge and a +2 oxidation number. And then on the product side, zinc is +2 and copper is 0, again because of their charges. So what that means is that copper is reduced, its oxidation number goes from +2 to 0, and therefore it's the oxidizing agent because it oxidizes zinc, and zinc is oxidized, which means it's the reducing agent. So again, zinc loses electrons by giving them to copper. Okay, and then this last one is pretty tricky. So I'm going to start with all of the other oxidation numbers other than that first chromium one, because that one's tricky. So oxygen is going to be -2 in our Cr2O7. Iron is going to be +2 because it's charged at +2. Hydrogen there will be +1 because it has a +1 charge. Iron is now +3 because it is a +3 charge. Chromium is +3, and then H2O we've done before. The hydrogen is +1 and the oxygen is -2. Now to figure out that chromium in the very first compound, we're going to need to know that the sum of the oxidation numbers of all of the atoms equal its charge. So we have 2 chromium atoms, so 2 times the oxidation number of chromium plus 7 times the oxidation number of oxygen, which is -2, will have to equal -2. So if we solve that equation, we're going to get that the oxidation number of chromium needs to be +6. So what that means is that Cr2O7 is reduced because the oxidation number of chromium goes from +6 to +3. And then iron is oxidized because its oxidation number goes from +2 to +3. So it goes up, it loses electrons, it's oxidized by reducing Cr2O7. So just in the interest of time, I want to go on to the very last topic today, which is balancing redox reactions. So we've talked before about how we need to balance what type of atoms appear on each side, but we haven't talked about charge yet. So if I show you...
There's a question.
It hasn't popped up yet?
Explain how electrons were lost and gained in the first question. Yeah.
Okay. So, sorry, the lag makes the questions a little hard. So for the very first reaction, magnesium and chlorine both start at 0 oxidation number. And then magnesium ends up at +2. So what that means is that magnesium has lost 2 electrons, and each chlorine atom has gained 1 electron. So magnesium has lost 2 electrons, which means it's oxidized. It lost those electrons by giving them to chlorine, thereby reducing chlorine. So magnesium is the reducing agent because it reduces chlorine. Similarly, chlorine is reduced by taking those electrons from magnesium, thereby oxidizing magnesium. So chlorine is the oxidizing agent. And then the same logic applies to the later questions as well. Okay, so back to balancing redox reactions. We haven't talked about charge, so we do still always need to balance the atoms on each side, but we also need to balance the charge. So if I look at this example reaction, it looks balanced, right? There's 1 copper on each side, and there's 1 silver on each side. Ag is silver. So my atoms are balanced. However, if I look at the charge, copper is uncharged on the reactant side, and Ag has a +1 charge, and there's only 1 of it, so we have a +1 charge on the reactant side. And then on the product side, copper is at 2+, and there's only 1 of it, so we have a +2 charge on the product side. And that doesn't work. What that means is that our electrons are not balanced. So what we need to do is change our stoichiometric coefficients so that atoms are still balanced. The atoms always still need to be balanced, but so that our charge is now also balanced. So now I have 1 copper and 2 silvers on each side, but my charge is balanced. I have 2 Ag pluses on my reactant side, so that's a total of a +2 charge, and 1 +2 copper atom. So that's a +2 charge as well. So just as one more example, I'll give you just really quick, just a couple minutes to talk about this in your groups. How would you balance this reaction? So it's already balanced with what elements are on each side, but how would you balance the charge? We'll come back together in just a couple minutes. Okay, so just in the interest of time, I'm gonna bring us back together, so finish your thought. Okay, so it looks like our atoms are balanced. We have one tin, Sn is tin, and one iron on each side. But we have a +3 charge on our reactant side and a total of +4 on our product side, so that doesn't work. So what I'm going to do is I'm going to put a 2 in front of both irons. So I need to put it in front of both so that our atoms are still balanced. So now I have one tin and 2 irons on each side. But now I have a +6 charge on each side, which means that my charges are balanced. So just sort of, when you're thinking about balancing reactions, like we talked about on Monday, kind of add this to something you need to check at the end. Most reactions that you'll balance will be like the ones we did on Monday where everything is neutral, but you'll have to balance some charged reactions. And when anything has a charge, you should just always check that electrons are conserved. That's what we're doing when we're checking that the charge on our reactants matches the charge on our products. We're making sure that electrons are conserved. Because if we didn't do that, and we had, a +3 charge on one side and a +4 charge on one side, that means an electron has just appeared or disappeared, and that doesn't work. Okay, so that is all we have for today. I'm going to end the stream in just a minute, and then go ahead and stay in the Zoom room. If you have questions for us, Katie and I will be around to